All right, so in this video lesson, we are going to study about directional derivatives and the gradient. Okay, and so again, in this particular topic right here, I am going to focus on the function of two variables. But then the concept and any method learned through the lesson here can be easily extended to the functions with more than two variables, such as function of three variables or functions of four variables. Okay, but so now let's get started with what it is by being a directional derivative. So we learned about all directional derivatives, but let's particularly find out what it is to be a directional derivative. Okay, and needless to say, this lesson here must be learned after you have already been fluent with what it is to be a partial derivative. Okay, so you must know what a partial derivative is in order to understand about a directional derivative. Okay, and so at this point, so in that way, now let me recall some past understanding. So now if we have, and again, just like what I was saying earlier, I'm going to focus on a function of two variables. So let's now have a given function f of x comma y. Okay, and so once we have a function of two variables, then anyone viewing this lesson should be comfortable enough with the idea that this function has a graph being a surface right above the x and y floor right here. Okay, so let me just draw a simple surface like that. It could be just a quadrant of a sphere or whatever, but so there we have a surface. Okay, so now there's a point on the surface. There's a point on the surface. Okay, and this point comes out from a point on the x and y floor being, okay, that point right there, some a comma b. All right, and so of course with this, so the actual point on the graph itself right here is at coordinate a comma b for x and y, and then the output value, the z value, is the function value at f at a comma b. So needless to keep going back too far into that. But now from that point, we are well aware, anyone learning this lesson is well aware that right from that point there is a tracing curve right along with the x-axis. Okay, and so we called, and then on that tracing curve right at that point we can find a tangent line, and so that tangent line here has slope. So the slope for this tangent line is our famous f of x, the partial derivative in respect to x. Okay, and so similarly, at this point, I'm gonna reconstruct the picture here, but clearing away some of the minor information. All right, so that similar picture, that same function, but let me make a different copy of that, of the graph. So in the x and y axis, okay, the surface for the function supposedly here, okay, and we have a point, okay, and that point right here, yes, a comma b comma f of a comma b. But right on that point belongs to a tracing curve along the y-axis. The y-axis is here, okay, and so right through that point on that tracing curve along the y-axis, there is a tangent line, and the slope of that tangent line is famously in what we already have understood. It's the partial derivative in respect to y. So there you go. It's a brief review of f's of x and f's of y. Okay, so. And think about it, I could have also drawn, I meant to draw maybe, because the two pictures, I'm not good enough to make the exact duplicate, but I'm talking about the exact same points, right? The exact same point located on the surface of a given function, a given two variable function. Then we can find f's of x and f's of y. We can find two different kinds of derivatives, two different partial derivatives. All right, so that's what it is. But now, all right, so now think about this case right here, the same function that we have as a given function. Okay, and I'm trying to put in the surface being the graph again. that same function with this surface as the graph. Okay, and then at that same point, a comma b comma f of a comma b, and on the floor, on the x and y floor, we have this point, a comma b right here. Okay, but now think about right on at that point, we are going to draw a vector, take a vector u right here, and now this vector u, this is the vector u. Okay, because from that point there can be so many vectors coming out from that point. So the first thing to keep in mind, this vector u is not necessarily parallel with the x-axis, neither parallel with the y-axis. So the vector u here is just some general directional vector right here. So the idea is now is that, what about along the direction of the vector u? Okay, along the direction of vector u, we can do the following. Think about if we can extend this vector into a line. Now you have to understand this line on the floor right here does not necessarily have to cross through the origin. Okay, the point is the vector u here is just point out from the a comma b points on the x and y floor and pointing out in whichever direction that is. One more key thing to keep in mind, the vector u that I'm describing here is a unit vector. All right, it's a unit vector. And then now we want to consider that behavior on the surface along the direction or in the direction of the vector u. So in this direction of the vector u, and again not really parallel with the y-axis and neither the x-axis, along that we can also draw a tracing curve that contains the point on the surface. Okay, we can draw a tracing curve that that's parallel with that goes right through the vector right here, but not necessarily parallel with the y-axis or neither the x-axis. And that tracing curve contains our point on the surface. And then so right at that, the picture is telling the story right here. Right at that point, we can find a tangent line. There is a tangent line existing, and we want to find the slope of the tangent line. All right, and so now with this tangent line right here, I'm going to make the following note. The slope of this tangent line, all right, the slope of that drawn tangent line right there is what we call the directional derivative of the function f of x comma y along the vector u. That's how we call it. That's how we understand what it is to be a directional derivative, okay, of the function along a given vector. Okay, and so along the way as you follow with the lesson, you will understand. You will catch the explanation of why we need this vector to be a unit vector right here. Okay, but so just a reminder, being a unit vector means the length of this vector u pointing the direction has to be 1. That's the fundamental understanding of being a unit vector. Okay, so I admit that my picture here may not be doing the job so well in terms of graphically illustrating. So let me turn on an actual picture, a real textbook printed picture that shows a very nice detail right here. Okay. All right, so here we go. This is the picture I found, and this picture can be found in so many different calculus textbooks right here. But see, neither this vector u right here is a unit vector, and you can see that according to the picture right here, it's starting out, and this picture is going a little bit different right here. I call this point here a comma b, but the textbook, the picture here is calling that the x sub 0 and y sub 0, and then of course being on the x and y floor, it's 0 out for the z value, and so this is the actual point on the surface right there, the point P at x0, y0, and z0. But see, just like what I was explaining earlier, now from that point right here, we are shooting out a vector at length 1, a unit vector at length 1, pointing in some direction other than the x-axis and the y-axis. And so along with that, see, there's a line, and now it's making the story even more clear that, see, the line, as we extend the line along the vector u right here, that line does not necessarily have to cross through the origin, okay, of the axes together. But now along that line, there is a tracing curve. And on this tracing curve, of course, containing the point on the surface right here, there is a tangent line. And so the slope of this tangent line right here is what I call it, the directional derivative in the direction of the vector u right there, or along u, the directional derivative along u. All right, so now as far as what that is, I would like to take it right there. That's how we define, and I'm staying away from what it being the fancy, the worded definition. So the directional derivative, once you understand what it is, we have a notation. So the notation here, and I think it's better that I use this board of mine. And I still keep the picture there so that as we're learning the new stuff, you can still always refer back to the picture. But it's a derivative. Directional derivative gets the notation capital D. Okay, so as far as notation, right, so capital D represents a directional derivative. We attach the function because, of course, anytime we're taking derivative, we're taking derivative of a whatever function that is. The directional derivative of a function in the direction of the unit vector u. That's what it is. Okay, so that's a notation. All the worded, the verbal version is set out the same way. The directional derivative, or a directional derivative of the function in the direction of that vector u. But instead of writing all of those verbal terms, we can now have one nice and short symbol, one nice and short notation. So that's what it is. I mean, that's a notation for that. All right. And so now back to the story right here, back to the idea. Okay, we want to now learn a way of how to calculate that, because there is a way to calculate that. And so my picture here is not doing so well with that, so allow me to keep switching back on the nice, clean textbook picture version like that, so that we can do a lot of work on that. Okay, so now the idea is as follows. In order to calculate the value, let's say at this point x sub 0, y sub 0, you see here's the trick right here, here's the key thing right here. You look right into this and it has that in the picture. So now I'm going to take a picture of this projection of the floor. Okay, I'm going to take the picture of the floor, just the floor, and I'm going to put it on my actual writing board. All right, so on the x and y floor, if the point AB is here, how about let's still stay with x0, y0, if that point x0, y0 is still there. And then the unit vector is pointing out this way. This vector is length 1. This is the vector u. So that, as we know up to this point about vectors, then this vector, any vector has two components, and let's call that A, comma B. Okay, so these are the two components. So I switch my variables names a little bit, my naming of the values a little bit. So the point is being seated at x0, y0, but then the vector is pointing in from that point A, x0, y0, the vector is pointing in the direction where A, comma B. Okay, and so now think about this. Back on the picture that I was showing, the whole idea is always about right from that point, if we pick an h distance, if we see, so that's why the picture here is describing it as the distance h. The distance h here is not necessarily the length of the vector u, because the length of the vector u is always 1. But h is some distance along this line. H is some distance along that line away from the point x sub 0, y sub 0. Okay, and so back on my board, I'm going to draw a different version. All right. So the vector u is here, but h may be a little longer. okay, or maybe a little shorter. Okay, so I draw that a little bit different with the textbook a little bit, but h may be some distance here. All right, h may be some distance there. But because of that, in the way it is, then with h being that distance, then when we draw a right triangular setup right here, then this horizontal distance here has to be h times a. And that is this vertical distance here, this vertical change of coordinates has to be h times b. All right. That is simply because, think about it, if we're using the Pythagorean theorem right here, then the square of HA plus the square of HB has to equal h squared. Okay, that is according to the Pythagorean theorem. And then let's check for consistency. HA all square is h squared a squared plus h squared b squared equals h squared, and then we can factor out the h squared right here with a multiply with a squared plus b squared, and that is indeed equals h. So this, I'm trying to show that this is the correct setup for each length, each length, the horizontal edge, and the vertical edge of this curtain rectangle, right triangle. Okay, and because see, this is the length of the vector u right here. This is the square of the length of the vector u, so it is 1. That's why we have a satisfying equality here. All right, and so now, after I have convinced you that if this length here is some h, right, some distance h right here, and so that length, once again, is the change on the x and y floor, the change on the x and y floor along this line right here, along the line in the direction of the vector u. So that change h right there can be expressed in components HA and HB in a right triangular setup like that. All right, so now after all of that explanation, here's the idea. Finding derivative, yes, it's a directional derivative. The partial derivative we've learned prior to this, and derivative that we've learned in count 1, it's all going to be in this one same concept. We need to calculate any derivative through a limit process right here. So that means what? This directional derivative is no exception. Any directional derivative in the direction of a given vector of a function f of x, comma y, can always be found by doing the following. In this case, the f of x sub 0 plus ah, comma f of y sub 0 plus bh produce a difference with f of x0, y sub 0. That's the difference. Because now with the picture being given here, now let me put the picture right at the little corner right here. But the idea is right here. As we have a change h on the x and y floor along the line here, then there's some change. See, there's some change in the value of the function. Okay, so this is f of this point right here, z sub 0, which is f of x sub 0 and y sub 0. But this point right here is f of x sub 0 plus ah, comma y sub 0 plus bh. This is the one. This point right here is that value. Okay, and so that vertical distance I'm having on the picture right now. Okay, this vertical distance, the picture here is not drawing it, but this vertical distance can be found by taking this difference, that subtraction. All right, and so now we have a difference, and then we divide that difference by, because we want to measure how much change over how much rise or fall, right? Change in y value, change in z value this times over how much run in the direction of the vector u. Okay, how much run, as you can see right there, how much run in the direction of the vector u. Okay, so over h. And then, yes, we're going to keep making h smaller and smaller. And so, hey, that is the limits concept right there. We're allowing limits. We're letting h approach 0. Okay? And so now after I put the picture away, this is the formula, one famous fundamental, to calculate the directional derivative value at that specific point, x sub 0, comma y sub 0. So allow me to actually, I should have had this, x sub 0, y sub 0. So this will come out one particular, the slope of the tangent line value right at that point. Okay, but now we want to extend this into a more, we want to extend this formula, this limit process into a more general. So now a directional derivative for any function at any point x comma y, no longer x0, y0. The point is we want to come out with some general rule. Okay, any directional derivative in a given direction of the vector u of a function f of x comma y can be found by f of x plus ah. Simply just that. We skip the x of 0, comma y plus bh. We take the difference with the function value at x comma y for any arbitrary x comma y value. Okay, and then over h. See that exact same difference quotient. Instead of fixing that to a specific point or a particular point right here, then we're gonna just come up with a general version for at any pair of values x comma y, and then we're gonna take the limit as h approaches 0, and that is the generalized version of the fundamental formula of how we can calculate the partial derivative. Okay, I mean the directional derivative at any general point x comma y. Okay, so there you go. That's the function right there. Okay, that's the formula. All right, but so now getting to the formula, I mean, look, using that formula as I introduced earlier is not easy, and it's taking a lot of time. So I am going to bring up one demonstration example. Okay, and this is probably the only problem where we use that, the exact formula using the limits, and then as we go through the limits, as we go through the limit process, we will recognize a more generalized way of finding any directional derivative, but without going through the limit process. Just keep thinking of the way the experience that how we've learned about taking derivatives back in the days. Back in the days, we started out learning and keep cranking through a lot of limit processes, and then eventually we hunger for an actual way to bypass all of the limit process, and that's what I'm about to do here. Okay, but I'm only for anyone learning in this lesson, you guys are mature enough that I only need to bring in one example where I have to ever show the limit process, and then after that, anyone should be flexible in math enough to recognize a general way of how we calculate a directional derivative without going through the limit process. Okay, so let's start out with that demonstration example. We're gonna say let's start out with a given function as following. F of x comma y equals, and the function I have here is xy squared. Okay, and then with that, we also given a vector about u equals square root of 2 over 2 comma square root of 2 over 2. All right, so let's quickly check. In your mathematical experience at this point, in your learning in math at this point, you should be quick enough to verify that this vector here is a unit vector. So save me from showing that on the board like that. Okay, do your math check to make sure you check that this is a unit vector, meaning length 1. Okay, but I'm suggesting that check. That's why I'm putting question mark right here. Is the length of this vector equals 1? You can quickly check on that for me. And it should be a yes, but hey, you're learning math here. It's not about whatever the instructor here is saying, and you have to believe it, be able to verify it on your own. Okay, so I leave that for students and viewers to verify that. But now I'm telling you that it should be equal to 1. It's a unit vector. Okay, so now our main goal is in that along that unit vector, and you can see that this vector is pointing in this direction. The y-axis, the x-axis, on the x and y floor, it's pointing in the 45-degree angle right there. Okay, and then wherever the point is, right now I'm just only pointing out that hey, this vector u is that kind of vector. All right, so now enough with that. we want to find, okay, we want to calculate. All right, and let's start using the symbol to formulate here. Okay, we want to find the partial, directional derivative of this function, okay, in respect to or along in the direction of the vector u given. All right, and so now I need as much space on the board as I can, so I'm going to erase out all of these extra detail right here. So here's the work. Yes, and like I said earlier, this is the only time and probably the only problem throughout the lesson that I am going to go through the limit process. But to start out with this, I am going to use this limit formula right here because the function, the example problem was asking us to find this d, right? This directional derivative of the function, the general one, because there's no x sub 0 and y sub 0 in the problem, okay, along the direction of the vector u right there. Okay, so I am going to use this formula, and feel free to pause the video or roll back to have a good look at the formula. All right, so to start out with this, I am one more time going to repeat the formula we need to use here. Okay, so the directional derivative for any function f of x comma y in the direction of a given vector can be done by taking the limit as h approaches 0 for f of x plus ah comma y plus bh, okay, minus f of x comma y divided by h. Okay, so it shouldn't be any surprise about what I'm doing here. But so now in that way, specifically for this problem, this vector u here has component square root 2 over 2 for a, that is square root 2 over 2 for b. Okay, so now I am further and further using that into the formula. And so anyone learning in this lesson is comfortable enough in math, so allow me to do the following. Okay, so that equals, now x plus ah here means x plus h times square root 2 over 2. X plus h times square root 2 over 2. And the same with that here. If we substitute in the components of the vector, y plus h times square root 2 over 2. So now here's how I'm applying this formula into our function along that vector right here. All right, we're going to produce a fraction. So x plus ah now understood at x plus h times square root 2. I'm looking at x plus h times square root 2 over 2, substituted in for x, and then y plus h square root 2 over 2 all squared, because y plus h over square root 2 over 2 is substituted in for y. And so we have this expression with the square. And I'm going to need to subtract x, y squared. And then we're going to, so that is the difference between f of x plus ah comma y plus bh. Okay, and then subtract by x, y squared. We divide by h. And this difference quotient here is going to be regarded as a limit problem where we're letting h approach 0. All right. And now with that, we're going to start using the algebra. We definitely don't want to directly use the basic limit laws here because it's going to give us a 0 in the denominator, a 0 limit in the denominator, and which we want to stay away from, we want to avoid. And so now we're going to definitely have to go through some algebra. Okay, so the algebra comes out as following. Now, for anyone learning in this lesson, you should be quick enough to verify my work here, but I'm about to FOIL out this perfect square here. And so you should be able to double check with mine and verify it for yourself how I come up with that final perfect square, okay, in the expanded form. So I'm still going to keep this x plus h square root 2 over 2 the same, okay, but that part here, and you can, if you're doing this on your own, you can also skip these some of these steps right here. I have y squared plus, okay, y h square root of 2 plus 1/2 h squared, then minus xy squared all over h we're taking the limit as h goes to 0. All right. And so now I'm going to advance to my other board. All right, so in that way, I am going to continue foiling out further. So with the two parentheses expressions that I've had earlier on the other board, and you can always roll back to that the video to see the other two expressions. But now, foiling out the two parentheses expressions, I'm looking at x squared, x y squared plus xy h square root 2 plus 1/2 x h squared. Okay, and plus, and now I'm looking at y squared h square root of 2 over 2. Okay, plus, and now y h squared square root of 2, and indeed that's going to cancel out, so just yh squared, okay, plus, and now I'm having an h cubed square root of 2 over 4. Okay, and then I'm subtracting. Let me write this a little smaller so that I have enough space. But then we need to subtract the xy squared, and I'm glad that I still have enough space. Okay, and then we're going to divide that entire difference here by h. And this is a limit problem where we're letting h approach 0. Okay, and so as soon as everybody is having a complete view of the complete expanded form, and like I said, you should be able to arrive at this as well along the way that I'm doing it. Okay, that's just a result of foiling out the two factors there. So now at this point I can cancel out these two opposite terms. Okay, and then anyone viewing this lesson is mature enough that I can start combining a couple steps together in one work right here. So after canceling out the two terms here, the two opposite terms, I recognize that there's a common factor h throughout all of these remaining terms. So let's cancel that out with this h in the denominator. Okay, so my next step here, I'm going to write down the simplified expression. Here we have xy square root of 2. That h got canceled away. Plus, now a 1/2 xh plus, and now we have a y squared square root of 2 over 2. The h is canceled away. Okay, and then here we got yh, and then here we got h squared square root of 2 over 4. Okay, and that's all we have, no more fraction. Okay, and then with that final expression here, simplified expression here, we take the limit as h go to 0. And now we're in a safe zone where we can start letting h approach 0 without worrying about dividing by a 0 limit in the denominator. So now here's what everything happens to be. This terms remain the same because it's independent with h. So xy square root of 2. Okay, and now this term is a 0. That term gives me a y squared times square root of 2 over 2. Okay, and then that term goes to the 0, and that term goes to 0. So this is what I have for my, yes, I call that the partial, the directional derivative of the function, of this beginning function in the direction of that vector u here with component square root 2 over 2 comma square root 2 over 2. Okay, so being able to get one done is just that. We have already come to the final destination here for that problem right here. However, there's more to see into it, because the point now is that we want to recognize right through this example a way to generalize the process so that we can bypass the limits work. We don't want to go through and crank through the limits work every single time. Okay, so now let me point out a couple of things right here. So just a little bit on scratch work. Now f of x comma y, okay, f of x comma y equals xy squared. Then so that means fx, the partial derivative of the function here in respect to x, is a y squared. Do you recognize that from here? It's a y squared. All right. And now let me even purposely rewrite this. So this was our final answer, but let me purposely rewrite it as a y squared times square root of 2 for a reason. I'm just switching the order, swapping the order of the two terms here. Plus, and now there's an xy times, okay. So xy times square root of 2, but I'm purposely writing that as 2 times xy times square root of 2 over 2. It's just some algebraic manipulation around here. I purposely did that to this first term. That's the reason. So now back to what I was doing in the middle of. If the function is x times y squared, then fx is y squared. Okay, and so we recognize that right here. So now that first term here, we're seeing that, hey, wait a minute, it's actually fx times, and what is this square root 2 over 2? It's the component of the vector. The component of the vector u. Or a. Okay, a is assumingly that we all agree that a is the component of the directional vector at this point. Okay, so I should have written that generally a. All right, plus, okay, plus. Now from that function, fy will be what? 2xy, the partial derivative of this function in respect to along the y-axis. Okay, is 2xy. 2xy is recognized right here. This is fy times square root 2 over 2. And that's why I purposely did that right at that moment when I did that earlier. Anyone watching the video was having no clue of why I did that. But now you see a reason. I did that to purposely, because I'm teaching here. Okay, so to purposely show you that, hey, this expression is indeed fy times, hey, and wait a minute, what is this? Square root 2 over 2. Square root 2 over 2 is also the other component of our vector u right here. Okay, or it's the b components. So now in that way, I recognize that this is f sub y times b. All right, so right there, ladies and gentlemen, we found the answer to the general directional derivative of the function along the vector u, but along that, we actually have found a way. Wait a minute, this is the new way right here, the revolutionary way without going through the limit process. All right. And so as far as the example that I brought up as a demonstration, we're done. And that example showed you how you can find the partial derivative, the directional derivative. But then right from that, through that example, we picked up the following important example, the formula. So anytime you are looking for the directional derivative of a function in the direction of the vector u right here, we now no longer need to go through the limit process. We just simply find partial derivative of the function in respect to x, multiply with a, the component. So let's suppose that the vector u has components a comma b. So now it's just f sub a times, f sub x times a plus f sub y times b. All right. Where the vector u has these two components. That's how we can do that quite easily. And so now at this point, you are ready to do any kind of examples where it points out some direct problem. Hey, here's a function, here's a given vector, find the directional derivative in the direction of the given vector. Okay, and so now a little bit of a side talk right here, but when it comes to directional derivative, I have to point out a remark right here. Okay, there are infinitely many directional derivatives. Infinitely many directional derivative, okay, at a given point. x0, y sub 0. Okay. Why is that? Quickly as a picture. And again, maybe I can bring up the picture that from the textbook, the much cleaner version of the text of the picture. You see, this is a point, x sub 0, y sub 0. This is only a vector, a unit vector pointing that way. But that's not the only unit vector. Who knows? I mean, we can have possibly some vector. We could have done a vector pointing this way. We could have done a vector pointing this way. We could have done a vector pointing that way. So there are infinitely many vectors pointing in all of the directions around in the 360 degrees directions all around that point x sub 0, y sub 0 on the x and y floor right there. And that's the reason why I was saying as a remark here, keep in mind there are infinitely many directional derivatives okay, at a given point right there. That's why, you know, in the topic of the lesson here, we're learning about directional derivatives. There are many of them, and anytime you're finding one, that's just you finding a directional derivative. Okay? So now, think even a little further. Wait a minute. If we're looking at a picture, let me now bring up a picture. You have already agreed with me up to this point that there are infinitely many directional derivatives. Then for any function at a given point. Okay, I'm trying to make dots right here. Then, wait a minute. So now all of a sudden I realize, hey, this tracing curve along the x-axis, okay? Yes, there's a vector pointing along that way. The tangent line here, the slope of that tangent line is f sub x. But wait a minute, isn't that one direction as well? So now the partial derivative that we use to understand is also understood as a directional derivative. Okay, that's along the x-axis. So what about right on that same line, right on that same point? If we're looking at the tracing curve along the y-axis. Okay, yes, right from the point x sub 0, y sub 0 on the x and y floor right here. Okay, then it is a direction pointing from that point to some direction parallel with the y-axis. And so, and then the tangent line right there has slope being f sub y, as we always know now up to this point. But so now f sub y is also a directional derivative. Okay, so as a bottom line, as a remark that we can put together, each partial derivative fx and fy, okay, is also a directional derivative. All right, and so that's the remark that we are looking at. Okay, and so, and again, keep in mind the length of the vector u here is conveniently 1. I mean, it has to be the length 1. So the reason for that, now you can understand that earlier, because when the distance h is the distance that we want to change according to the picture. And so the reason that we need this to be 1 because we only need some vector that points in the direction, but the length should be 1 so that any distance h can be expressed as, okay, the length of the vector, we always need that to be 1 so that any distance h, any change in h distance can be expressed as h times a and h times b here. That was the reason, but now I'm finalizing it. Okay, all right. And so now at this point, let's have a closer look at this formula right here. This is the formula, the famous formula to calculate a directional derivative of a function, right, at any given point along a given vector. And so now, right after looking at that formula, allow me to introduce for you what a gradient is. Okay, we're studying about the gradient. So gradient is a direct application or direct implication from studying about directional derivative. At least that's the way how I see it and how I have been teaching my students. Okay, so back to what I was saying earlier, I was looking at and focusing to the directional derivative formula. So let's specifically look at this part right here. Fx times a, f sub x times a plus f sub y times b. Yes, this is equal to, all this here is equal to the directional derivative, of the function f of x, comma y along the vector, the u with components a, comma b. That's not important. Let's look right here at this expression. Okay? From our understanding about vectors, from our learning about vectors right here, let me point out the following. I can see that why don't we purposely isolate out a vector as as f sub x, f sub y. And then there's another vector. B itself is already a vector. A comma b itself is a vector, which is a vector u. So now this formula I'm seeing here, all of a sudden I realize, wait a minute, it is the dot product between this vector u, the directional vector, with some vector that we define, some vector that we can purposely define. So this is something we recognize right through the formula. But now if we are purposely putting that in the vector setting right here, we realize, hey, we can create a vector, right? And components, the x component is the f sub x, and the y component is the f sub y. Okay, and I'm working with this specifically on function of two variables for now. Okay, and everything I've been doing is on function of two variables. But now the concept here can be easily extended to the function of three variables and more. But what I'm seeing here is, see, with the function of two variables, I can create the x components by doing partial derivative in respect to x. The y component is partial derivative in respect to y, and if we have a z variable, then we can create the third component on this vector by doing the f sub z and so on. But now, and I'll get back to that later. But here, I'm seeing this as a dot product. Okay, as a dot product. So now we just want to conveniently give this a name right here. We just want to conveniently give this a name. So now, ladies and gentlemen, this vector right here, like I said, we recognize that and we purposely now define it. This vector here is called, it's the gradient. Okay, it's the gradient. And of course, it's a vector already. Okay, it's the gradient of the function f of x, and we don't need, and needless to say, is the gradient vector. It's a vector. It's a vector because depending on the different x and y values substituted in here, each one of these is so far a function of x and y, and depending on the whatever pair of values that we put in for x and y, it becomes different vectors. So gradient of a function x comma y is a vector already. So needless to say, gradient vector or whatever. The symbol for that, okay, the symbol for that, a delta picture upside down right here. Now, the usual delta is like this in Greek, but this delta here is an upside down delta. So gradient of f, delta f, okay, or some textbook use grad f, okay, gradient of f, the delta f or grad f, but really verbally we say it's gradient of f, the gradient of f. Okay, and so the formal definition is given in any of your of the textbook that you're using. So I'm staying away from giving a wordy definition, but that's what it is, being a gradient vector. So that's the bottom line now. Okay, that f of x comma y, right, be a function. Okay. Then gradient of f is just simply created or defined to be the vector that comes out from that. Okay, or you can also put that in ijk components. Okay, so one thing you have to keep in mind right here, this function here, right here, that I'm writing down, that I'm summarizing as a definition right here, this function is a function of two variables. Then the gradient is a two components vector. Okay, so now be ready to extend this to the three variables or 4 variables the cases. So think about if you have an f of x, y, and z, for example, then your gradient vector is defined to be fx, fy, fz. Okay, it's a three-dimensional vector, and so on and so on. So if you have a vector of a function of 4 variables, then your gradient vector is going to be fx, fy, fz, and fk, whatever that you want to name your 4th variable. But it's a vector of 4 components. Okay, and so on and so on. All right, so that's how we define. So back to this particular problem here. That's how we define a gradient vector. So it has an impact doing this. Now it has an impact. Okay, let's now reshape our understanding on directional derivative. Let's now reshape our directional derivative. So yes, we learned just earlier, before we get into understanding what a gradient is, then this is fx times a plus fy times b, and I'm again specifically focusing on function of 2 variables. But you can easily extend this to functions of 3 variables and so on and so on. So that now means now I recognize another formula. So this is not new, but now right from that we recognize this as the gradient of f dot u right here. Okay, it's a vector. Gradient of f is a vector, and I'm writing the vector here. It's just me, but it's really optional. Okay, it's really optional because as I said earlier, being a gradient, you automatically understand that it's a vector. So it's a vector dot the vector u right here. That's how that's a different way of how we can think of a directional derivative. Okay, any directional derivative is the dot products between the given direction vector and the gradient of the function at that particular point right there. All right, and so at this point right here, at this point you are ready to do some examples so that you can strengthen your understanding. Okay. All right, and so now we're going to continue looking into some further properties of a gradient, because right now I'm only relating the gradients with the directional derivative, but believe me or not, believe me, it's going to have a lot more applications beyond working with directional derivative. Okay, and so let's look at some properties of gradient. Okay, so properties of a gradient. Okay, so now just dive right in here, this relationship, f dot u. Okay, this is equal to the directional derivative value. Okay, but then right in this dot product, we have already understood and learned that a dot product can be expressed as, or the value of a dot product equal to the length of the 2 vectors. So length of delta f, length of the gradient of f, multiplied with the length of the vector u, the directional vector, times cosine of theta. Okay, theta, cosine of theta. I mean, where did this theta come from? Now think about it. I mean, and right now I only told you so far that it's a vector, but you still haven't realized much. But a vector is something, in your understanding, a vector points in some direction. Okay, and I have not even given any graphical illustration of what a gradient vector is, but it's a vector. So let's say a vector like this, okay, on the x and y floor, okay, is some vector. And then the vector u, the directional vector where we take directional derivative, is some other vector. So of course, between any 2 vectors, there has to be an angle theta. Okay, the smaller angle between the 2 vectors. That's what this is. And right now, I admit, I still have not give a full graphical illustration of what the vector, the gradient vector looks like, but you just keep in mind that now if your function is a 2-variable function, then it's a vector on the x and y floor, and it's not necessarily pointing in the same direction with the vector u. It's not necessarily pointing in the same direction with vector u. That's why there's always some angle between them. And when they're both pointing in the same direction, the angle is 0. Okay, so keep some of those in mind right there, even though you have not had a full explanation about the graphical the interpretation of the gradient vector yet. We'll get that. All right, but so for now, at this point, as long as we know that these two are vectors, their dot products equal to this. Nobody can argue about that. Okay, so, but the length of u here equals 1. So that means we're looking at del f, or the gradient of f, the length of gradient of f multiplied with cosine. So this dot product will always equal to the length of the gradient vector multiplied with cosine of theta. But now, one more famous understanding from trigonometry. Cosine of theta, doesn't matter what value of theta is. Cosine of theta is famously running anywhere from -1 to 1. Cosine of theta comes out with output anywhere from -1 to 1. So we have this inequality. All right, so that should look familiar enough with anyone. And so now I'm going to multiply the length of del f to all three sides here. So I'm leading to having the length of del f times cosine theta will be less than or equal to, now on the right hand side I must also multiply that 1 with the length of del f. And then on the right, this is the right hand side, the left hand side is minus the length of del f. All right. And so now that means we're looking at, and all of this now, back to this line I was saying earlier, all of this now really equal to the directional derivative. Okay. So directional derivative, one big shock is that it equals to this cosine of the angle theta between the two vectors, the gradient vector and the vector u, and then it just simply multiply cosine of theta with the length of the gradient vector. But now let's look at this relationship right here in this inequality. It means in that I'm seeing that, hey, we have infinitely many directional derivatives, but doesn't matter where they are pointing. The maximum value for directional derivative, okay, is the length of the gradient vector. Okay, positive length of the gradient vector, and then the smallest, the lowest value, the smallest value that a directional vector can get, the directional derivative can get, is the negative of the magnitude of the direction of the gradient vector. This relationship right here is now going to give me the following conclusion. All right, so we draw out the following conclusion. Property number 1. So from now on we understand that a directional derivative, any directional derivative at a given point, right, can reach to maximum value being equal to the magnitude of the gradient vector. And then the lowest value is the negative of the magnitude of the gradient vector. That's the property right there. Okay? And so, and then I'm right here from that property, I'm going to open a remark right here, some remarks right here. So the maximum, okay, so the value reached, that's quantity as maximum, and reach this negative length of the gradient vector as the minimum. But now reaching the maximum at, so the maximum directional derivative is reached. Okay, so maximum directional derivative, it's a value, so that value is reached to maximum. It's reached when the directional vector u right here points in the direction of delta f. Okay, it's a vector, so if anytime that u points in the same direction, or in other words, in the world of vectors, when u is exactly parallel with pointing in the same direction with f, okay, parallel with f, that's where this value will reach the maximum, and the value for the maximum is this quantity. See, this is the magnitude of del f. This is the vector del f, the gradient vector. This is the this is the magnitude of the gradient vector. And so we can reach that maximum value anytime, only when the unit vector is anytime the directional vector is pointing in the same direction with that. Okay. So let me now, before I write down the next remark, let me really demonstrate what it means right here. Let's use this picture over here. Okay. So as I have pointed out that remark earlier, let's say if we have right there at one particular point right here, we can have so many directional derivatives because there are so many vectors pointing in the complete 360 degrees rotation around that point. So there are infinitely many the directional derivatives, including the partial derivatives fx and fy. But now, out of infinitely many of those, the maximum value, see, the maximum rate of change gets biggest only when this vector u points in the same direction of the gradient vector. Now we will have even a better picture of where the gradient vector is found at. Okay, but for now, just hey, if this particular direction on the picture here has already been the direction of the gradient vector, then this is the maximum. This is the maximum distance, the maximum rate of change. But that's just theoretically describing the idea right there. I still have not described the picture of the gradient vector yet. But see, throughout the entire 360 degree, whichever direction is the direction for the gradient vector, then anytime this vector u aligns with that in a positive direction, then it's going to reach the maximum value, the maximum directional derivative. And then if this is the direction, if this is the gradient vector and the vector u is pointing in the opposite, okay? So now let me get back on the board. All right, so the minimum value of directional derivative is reached, okay, when the vector u, the directional vector points in the direction of minus delta f, the opposite way. So when the vector u points in the direction of the opposite of the gradient, then we're going to reach the lowest directional derivative value right there. Okay, so that's the property number one of the two vectors, and right from this properties there are plenty of applications where you can see that through the examples and all that. Okay. All right, so now we are ready to look at property number two. But before I get into property number two, let me do a couple of demonstrations on the computer screen right here. All right, and I particularly focus this on a function of two variables. Okay, and then later on I will explain how we can extend this understanding into the functions of three variables or even more. But now to demonstrate the idea, let me start out with a given function here. Given function f of x comma y equals x squared plus y squared. Okay, with that function. So with a function like this, now we can find the gradient vector easily. Okay, that's for now, and you can treat this as, you know, some example can be similar to this demonstration one. Finding the gradient vector from a given function is simple. Del f, all we have to do is produce fx, fy. Okay, so fx here is 2x, fy is 2y. Okay, so now let's look at the nature of this gradient vector. And this example, illustration example, represents many other problems out there where, a lot of times you are asked to find a gradient vector. But so this is the reason why gradient vector is a vector function, okay, depending on values, the pair of values x comma y, okay. So for short notation, a lot of time people, and including me and many other mathematicians, write del f and del f, but really it's the actual vectors is found dependent on the x and y pair of values. Okay, so it's not just simply one particular vector yet. So there are infinitely many gradient vectors depending on where you're looking at, depending on where you're looking at, and that's what I'm about to illustrate right there. Okay, and now here's one more thing. So right here from that, so you found the general gradient vector, right? So let's look at del f at about 1, 1. 1, 1. Okay, so the value here is 1, 1. So I'm adding in that additional information right there. So that means we easily substitute this into the vector. So now at 1, 1, the gradient vector is this vector, 2, 2. But see, if we're looking at a different point, it will come out with a different vector. Okay, that's the nature of gradient vector right there. So the gradient vector does indeed changes its value, right, depending on where we're looking at the point. But now let me do a graphical illustration. Before I swing over to the computer screen, if at 1, 1 right here, if we're substituting this into the function, we're looking at z equals f of 1, 1. This is now function evaluation problem right here, which is 2. Okay, 1, 1 will give me a 2. So, but now, if I equate this 2 right here with the function, then I'm looking at x squared plus y squared equals 2. All right, ladies and gentlemen, if we bring back our understanding that we just learned earlier in this course right here, this is an equation, but relating this equation to that particular function, then this is a level curve. Okay, this is a level curve because an equation is a curve on the x and y floor right here, and at this specific level being 2, and I chose this 2 coming out from the output at 1, 1, but I purposely set that 2 as a level. So right at that level we have a level curve. Okay, we have a level curve, and this level curve contains this point 1, 1. Okay, and then now let's put it all together on the computer screen, and you're going to be fascinated. All right, so here we go. This is the level curve right here. This is the level curve at z equals 2. Okay, with the software I'm currently using, with the little program I'm currently using, I'm not able to put the label here that z equals 2 right on this curve right here to indicate that it's a curve at that level z equals 2. But in the end, it's a level curve. So the point 1, 1 is right here. Let's put that in. All right, and I can change the color to maybe black, okay, to make it a little more standing out. Okay, so the level curve is here. Okay, and then 1 is here. So now the gradient vector is this vector. Now back on the board right here, the gradient vector is 2, 2, but you have to understand this gradient vector has initial point at 1, 1. When you're studying about vector in general, usually it doesn't matter too much about where you put your initial point of the vector, because it only matters about the components pointing where, indicating where the vector is pointing. But now for the gradient, when we get into the gradient business right here, this determines where you place the initial point for your vector. Okay? So the gradient vector has to have initial point right here, and it's pointing out 2, 2 in this direction, in that direction. Okay? All right. So I am not able to create an arrow, but the arrow is supposed to be here. Okay, with this software I'm using, but this is now going to be our gradient vector. It's not this vector This vector is also 2, 2. That vector is also 2, 2. This vector is 2, 2. But what matters is this vector specifically is being seated at initial point 1, 1. And so right at 1, 1, we shoot out a vector 2, 2. So this is the gradient vector. All right. And this is the reason why, think about it, with the gradient vector like that, right? We have many other directional vectors coming out from this point, but that point's all around it. And this is the reason why, back on my board right here, this is the reason why back on my board I was saying earlier that we can only reach to the maximum anytime the directional vector points in the exact direction with the gradient vector. The gradient vector was demonstrated on the screen earlier. Okay, and then we can reach to the minimum directional derivative if our directional vector u points in the opposite way. Okay, all right, and so the further thing I want to demonstrate for everyone is that right on this picture, you see right at that point there's a tangent line. All right, right at that tangent line. So with this, the gradient vector is always in the formal, in a common popular term. Mathematicians worldwide say the gradient vector is normal or perpendicular to the level curve at that point, at that initial point, at that point on the level curve. So this point, once again, remind yourself that it's the point given in the problem right there. And then it creates this level curve, but then the gradient vector, of course, being initiated, being seated at this initial point right here, but it's also normal, okay, normal or perpendicular to the curve. But how do we categorize being perpendicular to a bent curve like this? It means if we put in a tangent line to the curve, to the level curve at that given point, then the gradient vector is always perpendicular to the tangent line at that point. Okay. And that is the property number 2 that I would like to get to, and for any of you guys at this point right here, as a bottom line. All right, so property number 2. In case of a 2-variable function right here, then the gradient vector at a given point, okay, so now I use x sub 0 and y sub 0, is normal. Underline that word for me. It means perpendicular. Normal to the tangent line, okay? To the tangent line of the level curve. All right, the level curve at that specific given point, x sub 0, y sub 0. And to be even more precise, I'm right now anyone learning this is at the beginning level, at the introductory level, so I don't want to bring in too much detail, but if you're looking at the picture even further, even a little more closely, then it's not only just perpendicular, not only just normal, but it's normal in the outwards. But since we didn't have a clear, categorized definition of what it means by being outward compared with inwards, then we're just seeing that through the picture. Well, a curve, right? A hopping, looping around curve right here has the outer area and inner area. So normally or usually the gradient vector points outward and being perpendicular, okay, to the tangent line at that given point. And so that's what it was stated in our property number 2 right there. But this is for the case of a 2-variable. So now I don't have a software that's strong enough to do the demonstration, but when we extend to the case of the 2 variables, okay? Think about it. If you have a function, f of x, y, and z, right? So the idea now is that the gradient vector relates closely to the level curve. Level curve when it was 2 variables. So now level. So now I explained earlier, back in those earlier days when you learned through the level curves and level surfaces. If a function having 3 variables, if it's a function of 3 variables, then this function will produce a level. Arrow of mine here means produce a function like that. And we set at a value k right here. It's gonna produce what's so-called a level surface. Okay, it's a level surface. Okay, and so level surface, keep that in mind. And so now we extend this property number 2 into the case of a 3-variable function, and even 4-variable function, or even more. But I can just stop at 3 variables. The gradient vector at x sub 0, y sub 0, z sub 0, see, function of 3 variables, is normal. All right, to the tangent. Okay. Yes, it's a tangent, but no longer a tangent line, tangent plane. All right, to the tangent plane of the level surface. Okay, level surface at the designated points x sub 0, y sub 0, and z sub 0. That's property number 2 right there. And then right here with this property number 2, you will be exposed to a lot of a good amount of example problems where it points out so many applications of how we can use this. Okay, of how we can use this well-known property number 2 right there. Okay.